So now that we've talked about the properties of acids and bases, I would now like to talk about some ways to kind of define them using some different scientist definitions and some different terms. Okay, first, what's the Arrhenius definition of an acid and a base? So for an acid, the Arrhenius definition, let's come up with the random acid HA, and A is just this make-believe anion, I suppose. So the Arrhenius definition is that an acid is something that produces H plus ion in water, and we really don't care what this is, but an acid will produce H plus in water, and we mentioned that acids technically or have that H plus floating around in solution. Now the Arrhenius definition of a base, and I'm just going to give it the random formula BOH just for base, and this could be any random cation, sodium or magnesium. So the base is going to produce hydroxide ions, which are OH minus ions in solution. So for back in the day, this was a decent start. Again, acids producing H plus in water, bases producing OH minus in water. But it's not really all-encompassing, and there's exceptions that might not work according to this definition. So we have kind of a little better way to really describe acids and bases than this. And that would be this Bronsted-Lowry definition. So the Bronsted-Lowry definition is a little different, and let me go through a few examples here. Let's take this reaction right here. So we would probably look at HF and guess like, oh, it starts with an H, it's an acid. So hydrofluoric acid. What happens when you put this in water or put it with water? So I want us to actually get this little double arrow going now to kind of show us that we're going to get some sort of equilibrium occurring here. So what happens is that this H goes with this H2O to form H3O+. We call this hydronium ion. So H3O plus is called the hydronium ion. It's almost synonymous with H plus, like almost. And I guess this would then leave the F minus on its own. So now we say that acids, according to the Bronsted-Lowry definition, are things that not make H plus in water, but donate protons or hydrogen ions. H plus is basically a proton. So again, the Bronsted-Lowry definition is that acids donate protons or H plus ions. Okay, so that would be my acid. So what about a base here? Again, we're forgetting about the OH for a minute here. So what happens if I have F minus reacting with water? And you're like, oh, I don't see an OH here. Well, let's see what happens. So now this time, I think the arrow is going to end up going like this. We're going to get HF over here, and now we're going to get that OH minus kind of kicked out. So we're like, oh, just like the Arrhenius, it is producing OH minus in water. So now the way to describe what's going on here, it's not donating. The word we commonly use is it's accepting or taking an H plus or a proton. Now these first two examples, you might look at them and be like, oh, it still kind of reinforces the Arrhenius definition of acids and bases. So let's look at a third example here that's a little goofier. So let's say I had this H2PO4 minus reacting with 2OH minus. Let's get a little double arrow here. And what if you saw this and you got PO4 3 minus and 2H2O forming here? So now you look at this reaction like, whoa, I don't see any H plus or any OH minus on this product side. So like, what's going on here? Well, let's focus on these hydrogens. So what's happening to get from here to here? It looks like these hydrogens are going with these hydroxides to form this phosphate ion and this water here. So if the hydrogens are going in this direction, I guess in this reaction, using the Bronsted-Lowry definition, we would classify the H2PO4 as an acid because it's donating hydrogens, and we would classify the OH minuses as bases because they are accepting those hydrogens or protons. So again, with the Bronsted-Lowry definition, I always want you to try and draw an arrow and then think about the words donate and accept. Okay, now this Bronsted-Lowry definition also brings up the concepts of conjugates. Now conjugates, I want you to think, are opposites in a way. So whenever you think of the word conjugate, I want you to think of opposite. And I really like that last reaction we just wrote out. H2PO4 minus reacting with 2 hydroxide ions to produce this phosphate ion and 2 H2Os. Now in this reaction, again, we already stated that the H2PO4s would be donating the H pluses to the OH minuses. So this would be our acid, and this would be our base. This, we could also say Bronsted-Lowry acid and our Bronsted-Lowry base. Now, what is a conjugate? A conjugate is like an opposite. And notice that in these reactions, I have this double arrow, which means that we have this reaction going in reverse also. Now let's go in reverse. Going backwards, what's happening? Going backwards, it looks like these waters would be donating hydrogens to the phosphate ions to turn back into that H2PO4. So going backwards, the hydrogens are going in this direction, which means going backwards, the H2O is a conjugate acid, like an opposite acid, and going backwards, the phosphate ions who are accepting those H ions are going to be acting as a base. So they are the conjugate base and the conjugate acid for this reaction. So again, when would we be using the word conjugates? Really only for these Bronsted-Lowry reactions. Okay, lastly, in the lab, we learned about the properties of strong and weak acids, but what do those concepts really mean? Now, I hope you started to memorize them. So a strong acid is something that dissociates completely in water. So if I put the acid HA in solution, what does it look like? Well, we always got some water floating around, and we have some H plus, and we have some HA minus. We wouldn't have any of this HA left. This means it completely separates in the water. So that's what strong means, is dissociates completely or separates completely. Now, what is a weak acid? A weak acid is something that does not dissociate completely in water. So let's use that same example, HA. Now I'm going to start out, I'm going to have some H2O in there. I'm going to have some H plus. I'm still going to have some A minus. This is an acid. It is going to separate somewhat. But we're still going to have some of that HA in there, because not all of it will completely dissociate. Okay, now lastly, what are strong bases and weak bases? It's the same idea. A strong base just means that that basic compound will be dissociating completely in solution. So let's say if I have BOH in water, let me get my water in there. It means I'm going to have B plus and OH minus. I'm not going to have any of that original, I would say, kind of still bonded substance in there. It completely separates. Versus a weak base. So the weak base would look similar. So if I have BOH going in water, let me get my water in there. I'm going to have B plus because it's a base. I'm going to have OH minus because it's this base. It will separate somewhat, but I'm still going to have some of that compound written as such. This represents that it is not completely separated or dissociated, is another word. So now that we've learned about the properties of strong and weak bases, and we've memorized which are the strong and weak bases, now we know what the strong and weak really means.